Good morning, folks. Just one more problem for us this week. In this one, we're investigating what the angle would be in order to pull a box along the ground using a minimal amount of force. Go ahead and pause the video if you need to read the problem description, but otherwise, let's get right into part A and start drawing the free body diagram of the box. Our coordinate system in this scenario is our standard plus x to the right, plus y upwards, so nothing new there. Considering our vectors, we have the weight of the box pointing straight downward, and the normal vector of equal length pointing in the opposite direction. And that takes care of the y-axis. In the x-axis, we have the applied force acting at an angle, as well as the kinetic friction pointing to the left to resist that pulling motion occurring towards the right. If we plug our angle in for f, now we can break that vector down into its components, where the cosine portion will act towards the right and the sine upwards. And since the box is being accelerated at a constant speed, there's no acceleration vector we have to include. So that's it for the free body diagram. Let's check out the sum of forces. If we start with the sum in the x direction, here's our expression. We can exchange the frictional force with mu sub k times n, and then move that term over to the right-hand side, like this. Since we don't know what the definition of the normal force is yet, we can do like we've done in previous problems and jump over to the sum of forces in the y direction and solve for it. All that's required is to take the two other terms and move them over to the right-hand side, like this. And now we know what it is. I have some empty room here over on the right-hand side of this slide, so I'm going to continue our work with this equation here over to the side, like this. If we plug that expression for the normal force into that x equation, here's what we get. The goal is to get f isolated, so let's begin by distributing the coefficient of kinetic friction into the parentheses. I'll move the term with f here over to the left-hand side, which will make it positive, and now we can factor f out and divide both sides by what's in the parentheses on the left. There's our equation for f that we needed to grab, and that's all there is to part A. That part's now done. In part B, our task is to graph this equation with the weight being equal to 400 newtons and mu sub k being equal to 0.25. And we're going to graph that from theta is equal to 0 degrees to theta is equal to 90 degrees in increments of 10. I used Excel to do that, and here's what my results look like. From the graph alone, it's a little hard to see where a minimum might be occurring. If we look, the minimum might be occurring somewhere in this area here, but it's too hard to tell. So instead of trying to figure that out visually, let's take a look at the data points over here. At 0 degrees, we start with 100 newtons, and then at 10 degrees, it dips down, but then when we go to 20 degrees, it starts going back up again. So it seems that our special angle has to be within this range somewhere of 0 to 20 degrees, or maybe even 10 to 20 degrees. But having a range of angles is not good enough for an answer. We can do much better than that. In order to find it, let's try out some calculus techniques. We'll go back to our force expression, this one, and the idea is to take a derivative of this with respect to theta, and then set that derivative equal to 0 and solve for the angle. The derivative part isn't so bad, and we can actually do ourselves a favor by factoring out the numerator, because mu sub k and w don't rely on theta at all. And for now, let's focus our attention on this part specifically. In order to complete this derivative, we'll need to use a technique called the chain rule. It's pretty similar to that U substitution trick that we used with integration in some of the past videos. Notice in this expression here, we have an inner function buried in the basement here, and the outer function is kind of like a 1 over something. Let's focus the attention on the innermost function and set that equal to a substitution variable, which I'll call u. We'll take a derivative of this u with respect to theta, and here's what we get. Pretty straightforward. Okay? You take a derivative of cosine, you get negative sine. You take a derivative of sine, and you get positive cosine out. So no special reminders required here. The chain rule says that we need to take a derivative of the outer function multiplied by a derivative of the inner function, with everything being rebranded in the form of u. Well, that's not too bad. Here's what that will look like. But one thing we can do to save ourselves on some of the thought process is to exchange the ratio form of 1 over u with an equivalent exponential form, like this. Now it should be apparent that we can use the simple derivative power rule on this outer function piece. When we do that, the negative 1 will become the new coefficient on u, and then we'll subtract 1 from this exponent here. Our result will look like this. So we have negative u to the power of negative 2 multiplied by this du over d theta stuff that we did earlier. Let's get this back into a usable form by converting from the exponential form to the ratio form that we had earlier, like that. Then we can distribute the negative into the parentheses and put the whole portion of this into the numerator, like this. Finally, we'll convert u in the basement back to theta, like that. And this is what we were looking for. But don't forget, when we were doing this derivative, we had that factored mu sub k times w part out in front. So if we include that, the complete form of our first derivative of f is this, here at the bottom. And earlier we talked about setting this derivative equal to 0, which is this step here. And the 0 on the right-hand side makes this incredibly simple, because we can divide both sides by mu sub k times w, and multiply both sides by the denominator squared, which just leaves us with the numerator being equal to 0. Move the cosine term over to the right, and divide both sides by the cosine of theta, and now we're free to exchange this trig ratio here with tangent, like this. Take the tangent inverse of both sides, and finally we have our angle. However, we're not quite done yet. Sorry to say. Part B wants us to find the value of theta that makes f a minimum, but in order to conclusively say that this angle results in a minimum force, well, we need to verify that. And here's how we'll do it. There's 3 cases to consider in this type of a situation. For case 1, it says that if the first derivative is equal to 0 and the second derivative is greater than 0 in the interval that we're investigating, only then can we say that f is actually at a minimum. In case you're curious, case number 2 is almost the same, but now the second order derivative is less than 0, resulting in f having a maximum. And finally, in case 3, if both are 0, well, then you have to pull some other tools out of your tool belt. But we don't care about case number 2 and 3. All we're focusing on is case number 1. So we've already completed the first part by setting the derivative of f equal to 0 and doing all that work. So now our job is to find the second derivative and make sure it's positive everywhere between 0 degrees and 90 degrees. To do that, all we're going to do is take another derivative of the one that we just completed, which will look like this. Like before, we can factor out the mu sub k times w term, since that doesn't play a role here. Again, let's focus our attention on this portion entirely for now. Unfortunately, this isn't a simple derivative that we can just do on our heads like the last one. So the question is, well, what do we do now? I'm going to introduce another rule that we haven't seen yet for derivatives, and it's something called the product rule. Here's a reminder of what that might look like. Whenever we take the derivative of two functions being multiplied together, the result is a sum that looks like this. We take one of the functions and multiply it by the derivative of the other, and vice versa, and then add them all together. You might ask, well, which function is f and which one is g? How am I supposed to know? As far as I'm aware, I don't think it really matters which one you pick. So in this case, I'm going to choose f as the numerator and g as the denominator. The derivative of f is fairly simple, and that can be done in our heads, right? Sine goes to cosine, and negative cosine goes to sine, so that's pretty cool. But it isn't so easy when it comes to the derivative of g. For that, we're going to have to apply another chain rule. Let's take a look at this closely. Our outermost function this time, it isn't like 1 divided by something, it's like 1 divided by something squared. And the innermost is, well, it's pretty familiar. It's the sum of the same trig identities as before. So what's great here is that we don't actually have to do a lot of work to complete this chain rule, because the innermost function is the same form as the first one we did. The u is exactly the same, which also means that the derivative of u with respect to theta is exactly the same. So that's cool. We can just copy the work over from what we did previously. All that changes is the derivative of this outer function in the chain rule. We can still do the same process, though. We will exchange the ratio form of the outer function with the exponential form, like this, which indicates to us, okay, the power rule still works here. The negative 2, in that case, will become the new coefficient, and we will subtract 1 in the exponent, resulting in this expression here. And I'll do the same kinds of steps as before, starting with distributing this negative into the parentheses, like this, and then we will switch back into the ratio form of u for the outer function, like that, as well as distributing the 2 into the parentheses, and then switching things back from u in the basement into theta. And that is what dg over d theta is. Let's go back to that slide that had all the pieces of the puzzle on it. Now we're free to get rid of this question mark here and plug in what we just did. So we have everything that we need now in order to write things in the proper form of the product rule. Let's go ahead and start that off. Here's the first line where I have g in the first part here, multiplied by the derivative of f with respect to theta, and the same kind of thing over here with f being this term, and the derivative of g with respect to theta being here. The first thing to do is to stick df d theta into the numerator of g on the left, and similarly with f into the numerator of dg d theta, like this. If you look closely at these denominators here, no, they're actually the same thing, minus the difference in the exponents. we can actually squish these together into a single denominator if we take this left term here and multiply it by a special form of 1. Okay? That will make the denominator have the same exponent as the one over here. And up here in the numerator, well, we're just multiplying the same thing twice, so we'll have squared upstairs. So now we have the same denominator on both sides, and we're allowed to just use a single one and add all the numerators together upstairs. Next, we can simplify this a bit by expanding things in the numerator, right? I'm going to FOIL out this squared term on the left, and then I'm going to do the same FOIL technique with the two terms being multiplied here on the right. When you do that, you should get this. It looks messy, I know, but there's really only 3 major players hanging out in the numerator now, and they're all in the form of cosine squared, sine squared, or mu sub k times cosine times sine. So that means that we can factor these 3 major chunks out, and if you do it appropriately, it makes the numerator look much nicer, like this. Before we call this complete, though, let's not forget that mu sub k times w term that we factored out earlier. If we put it all together, this is the final form of our second order derivative that we needed to figure out. What we need to do now is to graph it from 0 to 90 degrees. Again, the visual aspect of this graph doesn't do a whole lot for us. The derivative, well, the second order derivative, it blows up to enormous proportions close to 90 degrees. So the scale on the y-axis here makes it difficult to see if everything is truly positive across the board. So I've included the data points over here as well. Thankfully, I'm pretty sure that we're in the clear. Everything looks positive all the way down, and so we've demonstrated the necessary conditions for case number 1 and shown that, indeed, our force possesses a minimum at the angle that we solved for. Part C is just about done, but there's one last thing that we need to do. The problem description told us that we needed to evaluate the force at this optimal angle and see if it fits with what we did in Part B. Well, evaluating the force is easy enough. You know, if we just plug in the 0.25s, the 400, and the 14-degree angle, well, what do we get? It's just 97 newtons using 3 significant figures. But are we in the clear? Let's check the data points from Part B. Clearly, 97 newtons, well, that's in the neighborhood of the results around 10 to 20 degrees, but we can't say for sure if this is correct using increments of 10 degrees. So instead, let's investigate some values around the 14-degree mark that we found. Here I've taken 2 degrees above and below 14 just to be sure. And there's an extra significant figure in the force column this time because, well, if we only used 3 significant figures, all you would see is 97, 97, 97, all the way down, and that wouldn't be very helpful. So notice that we start at 12 degrees with 97.08, and then 0.03, then 0.01 at 14. Then the force starts rising again. So yes, this result does agree with our result constructed in Part B. Part C is now done. Let's recap what we did on the solution card. In Part A, we did our typical free body diagram and sum of forces analysis approach, which resulted in this equation for the force. For Part B, we graphed this equation here from 0 to 90 degrees in 10-degree intervals, and I would recommend referring back to that slide for the picture if you'd like to see it again. Not really much room to put it here. And finally, for Part C, we set the first derivative of f equal to 0 and solved for the angle, and this was the critical angle that resulted in the minimal force, which is why I'm calling it theta min. But we had to find the second derivative of f and check that it was positive across the entire interval from 0 to 90 degrees in order to say that this was truly the case. And thankfully it was. And when we evaluated f at this special angle, we found that the minimal force was 97 degrees to 3 significant figures. That's all for this one. Thanks for watching, everyone. See you next time.